We're going to talk about.
What's your name?
My name is Gladys, and we're going to talk about some space movies in inaccuracies. Mostly it's The Martian and Passengers space movies. So I'm going to hand off the mic to one of my friends.
Okay.
First error that we will discuss in the movie Martian is.
What's your name?
Oh, sorry. My name is Juliana.
Okay.
The first error we will discuss is the gravity on Mars. Like in this, since in the movie, we can see that Watney like moves as if he's on Earth, knowing that gravity on Mars is like the gravitational acceleration of Mars is around is 3.8 meter per second squared. We will see the calculation later. But first and foremost, how do we find the gravitational acceleration? We use this formula where G is the gravitational constant, and M is the mass of the planet, and R is the radius of the planet.
Okay.
And for the next part, here is the mass of Mars, and here is the radius of Mars. And we plug in those values from the previous formula, and we get 3.7 meter per second squared, which is about 38% of Earth's gravity. Knowing this, Mars is light proof that Mars gravity is lighter than what it is on Earth. So for the next we will use this proof as how Watney's weight or movement, like his jump height, differs from Mars and to Earth. So the first one is we will find the weight or the force exerted on an object due to gravity. We will multiply the mass to the gravitational acceleration. Since Watney's weight is not mentioned in the movie, we will assume that he is around 100 kilograms. So we will multiply 100 kilograms to the gravitational acceleration. So his weight on Earth, or like his force exerted, will be around 981 newtons. While on Mars, we will multiply 100 kilograms to 3.71 meter per second squared, and we will get 371 Newton, which is 62% less than his weight on Earth. Knowing this, he should be moving like faster, and it will be much doing work would be so much lighter. And the last part is his jump height. We will multiply we will assume that he can jump 1 meter, and we will multiply it to the gravitational acceleration of both planets, and we will divide it, and we will get 2.6 meter, and this one is his jump height on Earth, and that one is his jump height on Mars, which is twice as high than it is from Earth. So in conclusion, Watney should be moving faster, and everything should feel much lighter on him than, as we can see in the movie, he moves as if he's still on Earth, which is wrong. Thank you.
Okay, I think honestly, what is wrong? In the movie, they didn't do this. So what is wrong in the movie? Can you explain?
The way Watney moves in Mars, since he's technically moving as if he's on Earth, where he should be moving like faster. Any scenes on the movie?
Which one?
Yeah, I think any as long as he's on Mars.
Okay, maybe from mine.
Yeah, here we can see they're moving like as if like it's normal, like, as if like they're on Earth, where there is like already like a significant difference between the gravity between Earth and Mars. So there should be like significant difference between those two
Okay, so
gravities.
can you try to walk at the on the Mars?
So like you should be like you should be like 62% lighter than you are on.
Okay, can you walk first? From here to here. Go. Walk from here to here, can you?
Yeah, this is how we
Okay,
walk
you're
normally.
on Earth, right?
Assuming
On
we're
Mars.
we're
now,
on
now
Mars.
you're Mars.
We should be like faster, like
You're supposed to be 3 times higher.
yeah. Wait, we should be like 62% lighter.
Okay, so in your report, please explain. Okay, first of all, in your presentation, you should present a question at the beginning.
Yes.
Okay, what's the problem?
Yes.
Right? Otherwise, you just explain in words, right? And in report, please describe how it looks like to walk in the Mars.
Yes,
so
excellent.
what's the correct version of it?
The correct version. Okay.
Good.
Thank you, Professor.
Juliana, right?
Yes, Professor.
Okay. It was good. So, what's your name?
My name is Angel.
Angel.
Yes.
There's no Angel.
So, for my part,
Angeline. Angeline. Okay.
So in my part, I will be explaining about the radiation exposure scene from the movie, where this scene is the main character, Mark Watney, is using a radioisotope thermoelectric generator, or also known as the RTG. Now I will show you a brief clip. Minjem. So here, Mark Watney is planning to travel to move from a base camp RS4 to RS3 to RS4, I'm sorry, and he's bringing RTG with him in the back of the seat. What is the purpose that he did this? It was because he was traveling a 32,000 kilometer trip, so he needed something to hit his body up, and he was experimenting how he would survive during this 30,000 kilometer trip, and one of the problems was that the weather was cold at night, so he put the RTG behind in the back seat. Now, the RTG itself kind of looks like this. The RTG is basically an equipment developed by NASA, and what it does is that it has a chemical element called plutonium-238. Now, this chemical element is very unique because it can generate chemical heat, which is mainly used for as a substitute of solar panels, because sometimes when astronauts tend to travel to other spaces, they do not have enough solar light, so they exchange it with this machine that can produce heat. And fun fact, it has a half-life span which can last over 87.7 years estimated. Next slide. Okay, so before we get into what is the relation, we will briefly understand what is radiation dose. So how the radiation dose works is that there are two factors that I consider. The first one is the absorbed dose, and the second one is the dose equivalent. Now, we see the PPT, the absorbed dose itself is, the absorbed dose is the energy deposited by the radiation, which is in joules, over the mass of the tissue, which is our skin, how much our skin weighs. And the second one is the dose equivalent that we can get from multiplying the absorbed dose with the radiation weighting factor. There are two types. Value 1 is for gamma and beta, and 20 is for alpha. Now, the RTG equipment, it is an alpha radiation, so we will consider 20. Now, if we want to determine the energy absorbed per day, then we can do this formula by getting D, and assume that we have the energy deposited by the radiation is 1, and let's say for the lowest case scenario, the best case scenario, that he only got 10 kilogram of his skin tissue contaminated by radiation, because not all is exposed through the sun directly, we will get 0.1 mgy, and times 20 from the alpha weight, we will get a total of 2 MSV per day. And this is like the best case scenario, not to mention there are lots of factors that will increase the MSV of Mark, because in the movie, Mark only stays 80 days inside the base camp, and for the remaining 550 days, his base camp was broken. So that means his contact and exposure to radiation is much more, not to mention his suit also contains a lot of radiation that is collected. Okay, so the total radiation RTG would be 80 MSV. Next slide. Okay, so this is the last slide where I will point out the major concerns. Now, this one we have discussed that the total amount of radiation just from the RTG itself is 80 MSV, but what the movie fails to reenact that the main cause of the radiation is Mark himself, because he only survived 80 days with the HAP. The HAP is called the habitat when it's fully functioning, and the rest of the 515 days minus 80 days are broken. So he travels a lot in the movie. He always travels every day. He never stays inside, which means he never changes his suit, and it's exposed to radiation exposure. And let's say that this is still the best case scenario of cosmic radiation, only 0.7 MSV, which I can assure it will be more than that, times the total amount of 515 days is 360.5 MSV. Now, if we add this up together, it's around 440.5 MSV. Now, the fun fact, the annual limit for radiation of astronauts in NASA is only 250 MSV, and 250 MSV in Mars and in NASA is equivalent to 6-month trip travel. So can you imagine, like, more than this, and it's over 6 months. So it will be like double or triple more. So that's the main problem about the radiation, that the movie doesn't actually comprehend how dangerous the radiation is. And it's most likely that when Mark goes back to Earth, he would like have 5% risk of cancer or more. Yes, thank you.
Okay, that's it. Very good. But his suit is going to protect him from these, no?
Yes, his suit is basically just a normal clothes suit. It's not like a typical like Avengers movie suit. So like, and then the fun fact is that because he could change his suit every 80 days, but after 80 days the HAP shuts down, which means because of the storm, the equipments are all like broken and like it's all dirty. So he didn't change his suit. He literally just wears the same suit every day for the rest 515 minus 80 days. So I can get, and not to mention when he launches his space, he launches himself to space at the near end movie. He make a rocket ship, which is definitely not radioactive safe. Like the exposure from the sun and the cosmic radiation is much more than that. And we did not calculate that because it's such a rough estimation, but I can guarantee that it will be triple more than this.
Okay, very nice. Excellent, Anthony.
Okay, thank you.
Very good. Okay, next.
Hello everyone, my name is Sika, and I'm going to represent how Mark Whitney make the water to make the potato.
Okay. What is on his nose?
So he take the water from this machine,
Okay.
and then he started to make the water from hydrogen and oxygen.
Okay.
Okay, so for the first problem is the water existent in Mars soil. So the physics wrong is the Martians simplify the extraction of the water from Martian soil, but in this movie it simplifies the how he can extract the water from the soil. But in the reality, we have to use more energy and more resources to make this, and we can use this formula. Q equals to m times c times delta T, which is m is the mass of the water and c is the specific heat of water, and delta T is the temperature change required to release the water. And then this is the assumption. And first of all, we have to search for the energy to heat water from negative 60 to 100, and the result is 133.76 kilojoule. And then the second step is energy to vaporize water to 100 Celsius, and it's equals to 452 kilojoule, and the total is 585.76 kilojoule. So this value is the total energy for him to heat the water from the soil. And the next problem is producing water from hydrogen. So he produced the water by combining hydrogen and oxygen in an exothermic reaction to release the energy. And then, so the reaction will be 2 hydrogen plus 1 oxygen. And this will show how energy is released when water is formed. And then we can use this formula to calculate the released water. Use enthalpy change, which is Q equals to N times delta H, and the Q we assume that is 10 mole, and the delta H is minus 286 kilojoule per mole, and then we calculate it and get minus 2080 kilojoule. Yeah.
Okay. So what's the problem?
He wants to produce the water from hydrogen, but in the movie they didn't make it right from the physics theory. So
what if you make it right? What happens?
It should be used this, but in the movie he didn't use this calculation to calculate the hydrogen. Yeah.
Sorry, I don't get the point. What's wrong? What happens in the movie if he follows the physics law?
Because he didn't use the right amount of hydrogen. So
he needs more hydrogen?
yeah.
Okay, so he put more hydrogen, then it's okay?
Yes.
Really?
Then the total energy will be, yeah.
Do you see the point?
It's just the true calculation.
So you're saying you need more energy
Yeah.
to produce water, but then he has this RPG to create energy, no?
Yeah, because
That's not okay?
yeah, because he just used the small amount of resources and the
How
energy.
I mean, certainly nuclear reaction can create this, no?
Yeah. But then in the
Sorry,
movie,
I don't get the point. And what's the calculation in the previous page? You are calculating the heat, right?
yes,
So what's wrong in the movie here?
because he didn't explain how to extract the water.
He created the water or extracted the water
Extract
from
and
the
then
soil?
heat. Yeah, heat the soil. Then he can release the water.
Okay, then what about the hydrogen and the oxygen? So you're talking about two different methods?
Yeah.
Okay, and then what's the problem on this part?
It
So
just
you calculate the energy required, right?
yeah. So
Does
this
he
is
have
the
that kind of energy or not?
this is the energy to heat the water.
Okay, so what's wrong about it?
Because in the movie he just used the small amount of energy.
How small?
He didn't explain it.
Then you don't know how small it is, right?
Yeah.
You need to, so calculation is a method, but then you need to compare this number to draw a conclusion. That's physics. Physics is just not calculation, right? So you need to draw a conclusion from this number.
Okay.
Okay, so please clarify that in your report.
Okay.
Okay, and then you need to work on the presentation. You just show the calculation and then we don't get the conclusion. I think you want to say there's too much energy is needed to get the to
Yeah,
heat
yeah.
the soil to get the water.
Yeah.
And then also the next one, also you need too much energy to create water by combining hydrogen and oxygen. But then you need to compare this, please compare this number
To the
to
movie.
the number of the RPT or our daily life.
Okay.
How many, I don't know, how many gasolines are needed to create this kind of energy?
Gasoline?
Yeah. Or maybe battery. How many batteries needed? That's something to compare. Okay.
Yeah, yeah. Okay.
Please work on that. Okay.
Okay, thank you.
So my name is Teresha, and I'll be talking about the rotation of the rotation part of the Hermes, which is the spacecraft that the astronauts use to travel to Mars.
You, Teresa?
Yes.
Okay.
So as you can see in the previous video, when the circular was spinning, it looks like it's moving at like 2 rotations per minute, like really slow.
Okay.
Okay, next slide. However, like the astronauts can still like move like they're on Earth, like they can like stand somewhere, like there is still gravity, and like the scene aboard the Hermes spacecraft experiences Earth-like gravity due to the rotation of the spacecraft. However, the spacecraft rotation is too slow and the radius is too small to generate the Earth's gravity. And then when it comes to artificial gravity in a spaceship, it depends on the radius of the spaceship as well as the angular velocity of the rotating object on the outside of the spaceship. And then there are 2 forces that actually are involved in artificial gravity. First is the centripetal force, which is generated by the circular object outside of the spaceship, which like gives force to the center of the spacecraft to make sure that the astronauts are moving in circular motion and they do not fly off into space. And then on the other hand, while centripetal force moves inward towards the center of the spacecraft, there is centrifugal force which moves away from the center of the spacecraft, which pushes the astronaut to the walls so that they can walk on the walls as if they are the floor.
Okay.
So they work in different directions so that the artificial gravity can happen. And then like the calculations, the movie did not mention the radius of the Hermes, so I assume the radius of the object, which is from the center tube to the circular, is the radius is about 20 meters. And then the gravity that we want is 9.8 meter per second square. And then the angular velocity, we use the formula artificial gravity equals to the radius multiplied by the angular speed square. And therefore we get that if we want to generate the Earth's gravity as in the movie so that people can do their activities normally like the ones on Earth, we need the spacecraft to move at 6.7 revolutions per minute. We can also say as rotations per minute, so the circular object needs to move 366 times in the span of 1 minute so that the Earth gravity can be generated. Thank you.
Okay. So this topic is already discussed, right? Did you see that? A few weeks ago, somebody presented about this, right? So you need to compare and then do something more, okay? So please do so, okay? If you haven't done it, go back and watch the video and then compare with his result, okay?
Okay.
So just general instruction, if you talk about the same thing, you need to do better than previous one. And then compare with previous one and do something more than previous one. Okay.
Okay.
Okay. Thank you, Teresa.
Thank you.
Hi everyone, I was the one who opened the presentation just now. My name is Gladys once again. I'm going to present about the Martian storm in the Martian movie. Maybe we can skip ahead a bit. As you can see, like it's really, really dramatic in the movie. I'm sorry, I can't get into the camera.
So you're Grady, right?
Gladys, yeah.
Okay.
Yeah, and again, I'll show you once again. Yeah, like as you can see, it's a bit too dramatic, the storm in there, but of course it's a movie, so we gotta have the dramatic effect. So let's try to calculate the actual storm that's supposed to happen in real life. Like we can start from the atmospheric pressure. We should compare it to Earth because we're on Earth. For Earth, the atmospheric pressure is 1 atm, obviously, and Mars should be lesser than on Earth because Mars has less gravity and stuff like that. But how does it correlate to the storm? As you can see, the astronaut, they were like trying to fight off, resist the storm, right? So like, obviously it kind of relates to the force exerted to the astronauts. And logically, according to physics law, you can like kind of assume that less pressure means less force exerted according to this formula, F equals pressure times the area surface area. And then I should probably give you more information about the wind speed in Mars. So we're just going to assume, according to NASA, like the usual Mars storms, it kind of gives out like 100 km/h wind speed. But of course, for dramatic effect, like shown in the movie, we're going to assume that it's 160 km/h.
Okay.
Okay. And then I kept on talking about pressure, because I want to do the conclusion based on the dynamic pressure, the wind dynamic pressure, in the case of 160 km/h wind speed. So this is the calculation, yada, yada, yada. You can see that if we use that 160 km/h and then use the wind density, I'm just going to assume things here because, well, the movie didn't really tell me like what is the exact number, but we're going to assume in the real life cases. So on Earth, maybe the scene shown is more accurate because as you can see, the comparison, like on Earth is really large, PA. And then on the Mars, it should be this less, like what is 10K to 1 ratio. So as you can see, the pressure is really, really low, so that the force exerted to the astronaut should be not as significant as shown in the scene. So like in the scene, maybe I should reenact, like what should happen. Like in the scene, the astronaut, they're using suits, so like they have this protective thing, and then in real life, they should be like this. Like they should just walk fine, honestly. But in the scene, they're like, fighting off the wind and stuff like that. So I can conclude that the scene is a bit too over-exaggerated.
Compared. How did you get the mass density?
Oh yeah, this is the wind density on Mars. Like I just took it off from the, sorry to say, but I sourced it from Wikipedia, which is not that.
Okay. So
yeah.
It must be realistic.
Yeah.
Okay. Good. Very nice.
Okay. I should hand off to the next person.
Okay, that is very good. Who's next? Oscar?
My name is Oscar,
Okay.
and my topic is similar with my group member. I just found it lately, and and we can see that when the spaceship the spaceship doesn't have power, so there is no gravity, and all the thing flows up. And when the spaceship regains power, the gravity comes back instantly, and this is not true in real life. So now I will use my calculation to explain this error.
Okay.
If you want to make artificial gravity, you have to spin the spaceship, and you have to spin the spaceship in uniform circular motion to produce centripetal force. And if you use the correct parameters, you can produce the same gravity as Earth on the spaceship. So I assume that the diameter of the spaceship is 10 meters, so the radius is 5 meters. And because we want to produce gravity, so the acceleration we use 9.8 meter over seconds square. So we just plug in all the numbers in the equation, and we get the t is 4.5 seconds. That means we have to rotate 4.5 seconds. That means the period is 4.5 seconds. So if we want to get this steady, uniform circular motion, we have to wait at least 4.5 seconds to let the spaceship spin, and we can get steady gravity. But from the movie scene, we can see that when the spaceship regains power, and the spaceship got gravity instantly. And this is not right, because we should wait that long to produce gravity. Yeah, so that's all of my presentation.
Okay. Well, I have the same comment to Teresa, right? So
Yeah.
you need to compare with previous student presentation. Okay. And also, I give you a homework, both you and then Teresa. Please consider how big is Coriolis force, and then what happens to the people living there. You know Coriolis force, like the Earth is rotating, right? So if you throw a ball from North Pole to South Pole, ball is going to go move, right? It doesn't go straight because Earth is rotating. And that's going to be very big in this kind of space station with fast rotation. So calculate how significant this effect is. What happens if you throw a ball in a station? Okay?
Oh, okay.
Okay.
I'll try.
Okay.
Okay, so hi everyone. I'm also doing the Passengers movie, just like my teammate Oscar. My name is Jennifer.
Okay.
So I'm going to be explaining the main plot of this movie that is actually problematic. I'll skip ahead. So the whole story is that there's a spaceship containing passengers, which is like all the humans on Earth. They want to live.
This is the same movie or different movie?
Oh, the same movie with Oscar, the one with the water scene
But
before.
this is not about Mars and
We
Martian.
did
Oh, no,
because
two movies.
We have so many people.
Yeah.
That's fine.
So, wait. So yeah, this is.
Star is passenger.
Yeah, they contain like a colony of humans in this spaceship called the Avalon. So, this spaceship is like automated. It's just flying out of space. And one day, it somehow encounters, It encounters like this nest of asteroids coming at them. And first of all, I want to say that in space, it is kind of highly unlikely for you to suddenly encounter like flying asteroids hitting your spaceship. And then the main part of this movie is that, suddenly there's this huge asteroid that's traveling to the spaceship and hitting it right at the epicenter. If I'm not mistaken, it's the fusion reactor. So it just hits the spaceship this way and shakes everything. And because of this asteroid, one passenger wakes up because there's a malfunction in the system. Okay, so the part I'm going to talk about is how unrealistic it is for the asteroid to hit the spaceship, but then just leave a hole in it, leave a dent in it. Well, in my opinion, from my physics calculation, it's supposed to actually obliterate it. Why? Because if we count the kinetic energy of the asteroid hitting the spaceship, which is used in this formula, first of all, we need to calculate the volume of the asteroid. So, actually, it's not mentioned in the movie, but I'm just going to assume the asteroid is that huge and the spaceship is that huge. So the asteroid is like 50 meters long with a radius of 50 meters. Let's assume it's that big.
Yeah.
And the radius is 25 meters. So we plug it in the volume. The volume is, after calculating, is 65,450 meter cubic square.
Okay.
And then we calculate, obviously, the mass, which is the volume times the density. And we also assume the density is, actually, I just Googled this. The density is about 3,000 kilograms per meter square. And we get the rough estimate is 196,350,000 kilograms. We plug it in the kinetic energy formula, and this is a long calculation, but I found 39.27 times 10 to the power of 12 joules. So after getting this calculation, I compared it to other energy of explosives that we know, and one of them is the TNT. So one TNT explosion, the kinetic energy is, I'm sorry, I didn't write it here, but it's 4 times 10 to the power of 9 joules. So if we compare it to this, to the explosion of the asteroid hitting the Avalon in this movie, it's equivalent to about 10,000 tons of TNT exploding. So the ship should have actually obliterated.
Right.
The movie should end credits right there and then. Yeah. So that is my observation from this movie. And next.
Is it really that big?
It is exaggerated that big.
Is it really 50 meters? How big is the spaceship?
It is not mentioned. That's why I assumed it's 50, because it contains the whole human colony, so the entire Earth. So I'm assuming it's very big.
How big is the asteroid?
50 meters.
So maybe can an asteroid be smaller?
Yes, it can be smaller, but still leave that big of an impact.
Is there a scene that the asteroid hits the spaceship?
Oh, yes. Wait. These are the smaller ones. And wait, this. Yeah, so collision alert, and then.
Oh, so you think it's as big as the spaceship? Okay.
Yes.
Okay, good. Good observation.
And okay, vocab. And we actually have some physics vocabularies. I'm not going to explain all. One of them, some of them are already explained indirectly by my teammates, like uniform circular motion, exothermic, enthalpy, radioisotope thermoelectric generator. And then maybe it's not mentioned, but my teammate Angel used the term millisievert. MSV is a unit to measure the dose of radiation absorbed by living tissue, and centrifugal force and centripetal force. That's it from our presentation. Thank you for listening, and we will now play the Kahoot.
Okay, very good, Daniel. Then we move on to Kahoot.
Please join, guys.
Okay. Please join quickly. We are running out of time, I guess. Okay, people, Jayo, you need to beat all the people. Okay? And you guys, please don't join, because you guys know the answer. Where's Iron Man? Okay.
Got internet connection.
Join. You're the enemy here.
I will join. Wait.
Okay, shall we? Okay, you want to join?
See, connecting complete.
Okay, let's
It
start.
just started.
I'm sorry.
No connection.
Only one person got it right. Oh, Iron Man is in.
I'm coming back.
Okay. Oh, A. Oh, you're number one until last one. Who's A? Who's A? Ah, close. So you get the bonus point. Okay. Thank you very much for group 12. Was very